In this video, we are going to talk about shortest path problem in graph. In a shortest path problem, we are given a weighted directed graph with weight function W, mapping edges to real value. The weight WP of a path from V1 through Vk is the summation of all the edge weights along in the path. A shortest path corresponding to a path which has minimum weight. We use theta to represent that. If there's a path from U to V, then we say the theta is equal to the minimum path weight if U is reached to V, right? If it's not, then this is assigned to be infinity. Shortest path problem could be represented in different format: single source shortest path, single destination shortest path, single pair shortest path, or pairs shortest path. In this four shortest path problem, if you had a solution for one, then you can adapt it to solve all the other three problems. And also in this, all these shortest path problems, they are common property. The first one corresponding to optimal substructure property. This corresponding to give a path. If that is the shortest path, then all the subpaths of shortest path are also shortest paths. We use Pik to represent a shortest path from Vi to Vk. We use Pij to represent a subpath Pik from Vi to Vj for any I and j. Then Pij is also shortest path from Vi to Vj. This can be proved by the contrast method. Let's say Pij, let's say P1k. Let's change the color. Let's say P1k, right? This is the shortest path from V0 through V7. Or let's say from here, right? From here. From here to this guy, right? So this is equal to which V1, V2 plus, since it's the shortest path, right? So we say this is the P25 plus with V5, V6, right? Now, if you say this is wrong, this is not the, if this is wrong, this is not the shortest path. You find another shortest path can reach from V2 through V5. And then you name that is one as P'25. Since this is smaller than P25, right? So you replace this one. So you say, okay, we have P1k prime, which is equal to W V1, V2 plus P prime 25 plus W V5 V6. Since this one, it is smaller than this one, it is larger than the P prime. So we say this is also larger than Pik prime. So this is the contrast. We say this it is the shortest path weight. We already claim it is the shortest path weight, but later you find out even better shortest path. In that case, this is a contract in conflict with the assumption. In the shortest path, usually we talk about it is a positive. If your shortest path includes a cycle, usually we ignore negative weight cycle, which corresponded to if a shortest path include negative weight cycle, this shortest path is not well defined. We do not, all this algorithm we talk about, we do not cover for this negative weight cycle in graph. The reason it is, we can always get a shorter path by going around the cycle again and again. For example, we have this PSV and the shortest path, right? We want to calculate this one. And so one of the time point, we get this one for one round. We have a specific, let's say this is the U, right? So we have a PSU plus, so what we have PUU, right? Because it's a cycle. And a plus PUV, right? And so this is the first round. If we have a second round, then in that case it is PSV plus, since this is negative, right? This is negative. And this negative will cause the whole thing here, it is smaller. So the whole thing here, which is smaller than, this is smaller than this one, right? For the second round. So the second round, has a smaller than this one. And you can imagine if you have many rounds, for example, n round, right? And this will be n go to the infinity. In that case, this will go to the negative infinity, right? Can you imagine? Good. And this figure we used to prove that, just as what we discussed, the difference is we use shortest path weight from source S to counter loads. We label this one inside of each vortex. The start loads has the shortest weight from S to itself, which is 0. And this number 3 corresponds to the shortest path from S to here. And this is shortest path from S to B through A, right? And then take a look at this one. Here we have, take a look at this branch, and then we take a look at this branch. In this branch, we have a positive. This is a positive cycle. In this positive cycle, we say definitely the first round of this cycle gave you smallest value, smallest path weight, only in this branch, right? The question here, it is, this have another branch. This branch, it is shortest, the negative, this is a negative weight cycle. So in that case, as what we prove, and from S to G will be negative infinity when we go around this negative weight cycle for n time, n go to infinity. And this is the same, right? It's the same. So it should be negative, negative, and negative. Okay, so now I wanted to move to the next slide. The second property, which is we use a lot, this corresponds to triangle inequality. For a given vortex S in V, and for every edge UV in E, we say the shortest path from S to V is smaller than or equal to the shortest path from S to E plus the edge weight. This corresponds to the optimal shortest path of S to V. If you have another path go through U, then in that case, the shortest path should be smaller than we use this U, or if this shortest path from S to U should be upper bound by the shortest path weight from S to V cross U, right? So we guarantee this shortest path, since we need to reach from S to U, if we need to go through U, in that case, so we say shortest path should upper bound by that. should the upper bound by the shortest path from S to U plus the edge weight from U to V. And such that if you have many, think about that, right? If you have many these different vortex and can help you reach from S to U, you want to make sure that you get the smallest one. You get the smallest one. You want to get the minimum one. So this will be minimum. This will be minimum of all this SUI plus UIV for all paths I from S to V through UI, right? So we extended that, right? So it means no, the SV, it is smaller or equal to. Smaller to equal to the minimum of every this specific path, which is through the UI, right? This also tells us we have to check all this possibility and get the smallest one. When we need to check the one-step relation, two-step relation, and the more-step relation. And then so that is the minimum amount all these different steps and which cause S can reach to V, right? So this is a very useful property, also called the triangle equality property, and it can be extended to what we talk about the relaxation. So maintain in this relaxation procedure, we use dV to represent. We use dV to represent the upper bound on the weight of a shortest path from source S to V. We want to find the closed upper bound, the tied upper bound. And dV is called a shortest path weight estimate, and it's upper bound on theta SV, right? So from the source. And this we check for single source first. And all pair shortest paths can be reduced to the single source path from every node as a source, right? And then so we initialize it. For every vortex, we initialize to be infinity in the beginning because we need to find the upper bound. And then so we set up the parent vortex of V to be long in the beginning, and the source, the distance to the source node is 0. The relaxation UVW, and UV it is 2 vertex, and W which corresponding to array of the weight. If dV is larger than du plus WUV, then we want to reduce the shortest weight. We sign the du, which is the distance from source to V, is assigned to be du plus WUV, and pi V is assigned to be U, the closed parent in the shortest path. And take a look at this one. We say 5 and 6, and this the number here, each nodes hold for the distance from the source S to U. And such that, so we have S to here, right? And we have S to U. So this is the shortest path. This is the dV we represent in the vortex, and this is du. And add up du plus 2, which is smaller than this one, and such that we say the shortest path from S to V can be better if we go through U, right? If we have a shortest path from S to V, go through U. So this is relaxation. And take a look at this one. In this case, once we have du plus W UV, in that case, this is the equal to 7, which is larger than 6. There's no change. The process of relaxing edge consists of testing whether we can improve the shortest path to V found so far by going through U, right? If so, updating dV and pi V. A relaxation step may decrease the value of shortest path estimate dV and update V's predecessor's attribute pi V. So this one tells us, and if we consider one-step relation, and if we consider the two-step reachability, in that case, we may reduce the shortest path weight. So in that case, that help us design a different algorithm. Now let's take a look. The properties of relaxations. Algorithm differ in how many times they relax each edge and the order in which they relax the edge. Based on these two, they could get different questions. And let's take a look how many times each edge is relaxed in BFS. In the BFS, the traversal order, we access each node for only once. And let's take a look at this one, right? Let's see, this is S, this initially be 0, and here this is a 3, this is a 5, this is a 4, this is the, let's see this one, right? And this is the 6. So when we take a look at S, we see that we have the Q, and we have S ended in Q, and we delete that, right? And then we have A, B, C, and D. So we have A in Q, and then the A will be gray color, and S to be let's put the color here, right? Let's put the color here. So S, it is black color, and A, which is the gray color so far, and then after that it is you have B in Q. B is also gray color, and then you have C and Q, right? C and Q. C, it is also gray color now, and then you have D and Q. D also gray color. So this is the S, A, B, C, D. This is the color, right? And then so okay, I think we jump a little bit. So we have A, D, Q, right? A, D, Q. We have C and D and Q. So since A, D, Q, A is a black color. And also in this procedure, we say S, this should be 3, right? And then after that it is we DQ this one, and this is the distance, which is a 5. And then we'll go to here, go to this one, because this is the B reach to this guy, right? B reach to this guy. And since this one, D reach to this guy, so before you push this one to here, you have a 7. Now when you go to here, you change this one. So this question asks you how many times each edge is relaxed in BFS, each edge. And from what we discussed here, you can say each edge got relaxed for only once, because each edge you access for once. And through this BFS, and you can get shortest path from root node to every other reachable nodes, right? So now here you can continue to finish this BFS. So with algorithm differ in how many times they relax each edge, the order in which they relax edges. This also helps us to say if we use some way, if we can relax the edges less and we can get the shortest path from the source to every another node, that will be very good, right? And in the BFS, since they make the specific order and such that they do not repeat, relax some edge. So this is a good solution, right? Now let's take a look. Let's take a look specifically single source shortest path. Shortest paths are always well defined in DAG. DAG corresponding to directed cyclic graph, corresponding to directed graph and also low cycle. What we showed here in the previous slides, what we showed here, if we do not ignore direction, which is a directed cyclic graph. And if we ignore direction, which is undirected graph. Undirected graph is good for use BFS for undirected graph, because every edge just relaxed for once. And since in the undirected graph, for each edge, which represents two directions, and use BFS, you can just access this undirected edge for once. So this is very efficient. For directed graph, and we want to take a look to say if we have a better solution than the BFS. Okay, and then this idea it is if we are lucky, the process vortices on each short path from left to right, we would be done for one pass due to what we talk about, the triangle inequality, right? In a DAG, keep in mind, DAG corresponding to directed acyclic graph. Every pass is a subsequence of topological sorted vortex order. If we do topological sort and process vortices in that order, we'll process each path in a forward order. Never relax edges out of a vortex until have processed all the edges into the vortex. Just one path is sufficient for DAG, for the directed acyclic graph. Okay, let's take a look. And what is topological sort? Topological sort is corresponding to the DFS. You use DFS to traversal the graph and you list all the vertex in this DFS the working procedure, right? Let's give you an example. Let's say A, go to B, go to C, and go to D, and go to E, right? We use the same graph to discuss. The topological sort in this case corresponding to from A, we reach to B, right? And from B, we reach to D. And then we reach to what? We reach to E again, right? Because we have to make sure, not this one. We have to make sure we go as fast as we can, and then if there's no place to go, we go back and then reach to as fast as you can, right? You don't want to go back, you want to check as fast as you can. And if there's no place to go, you go back. Then you check another branch, go as fast as you can, right? Then you go to here, right? And then you say, okay, this is what you visited. And such that the topologic order of this one is A, B, D, E. Then you go to the C, right? It's use different color. So then you go to the C, and this is C, which is go to the here, right? Go to the here. And of course, you have a B to E, we already check. B to E, we already check, right? It's A to C. 1, 2, 3, 4, 5 edges. And then, so you have C. This is C to E. And for this edge, this is C to E. I wanted to use this way. to say this guy, right? This guy. So this is a back, no, this is some edge which access the loads has been already visited. It's a black edge, right? So this is the back edge. This is the forward edge. This is the forward edge. Okay, and then so you use this topological sort and get the order of all the vertices, and then so after that, okay, I go back to these slides. Give me 1 second, and let's finish this part. Okay, and then so you use the, let's see, do we keep any writing? Maybe not. Okay, I see. So we form this topological sort, right? And we get the order of all the vertices. And then after that, it is initialize relaxation G from S starting node. And for each vertex U, taking in topological sorted order and do, this is in, right? In. This is the different tools I used in another machine. So this is reason they change this character. And so for every vertex, you take in topological sorted order. And then for every adjacent vertex, you do relaxing, right? As what we show you, and in the previous one, in that case, use this way, you can visit every vertex for once, and you can access every edge for once by follow this order. You do not repeat some specific edges. So in this way, this is a very good way. And from when you check this one, you find that the algorithm here, the runtime of this one, is equal to the runtime, right? The runtime of this one is equal to O what? OE, okay? So let's take a look. And give you an example. So this is the source S, and this is all another vertex. And since maybe some loads, maybe it is isolated, so this reason you add one SR, and this is from initialized to be infinity, and this S is initially be 0, and then you go through this one to check. So you check T, relax this one, you got a 2, right? Let's go to another slides. You got a 2, and then you continually, you go as fast as you can, then you get the, take a look at this one, right? You get a 2, and also this edge from S, you relax it to be 6. You check all the adjacent edges, right? And then after that, you access this vertex, and then you change the Y and Z, these adjacent vertices, and relax it to be 6 and 4 through these two edges. Now you go back to 6, and then you based on this 6, you check, and you may find that the previous one, this number plus this number larger than this number, so this edge will not help this one, right? And then after that is you check the adjacent edge, and then you reduce this one to be 5, and this one do not reduce. And then so after that you check the vertex file, and this is reduce this guy, right? And then after that it is you finished this shortest path from a single source to from the single source to destination. This is the R corresponding to another vortex. Okay, and the shortest path in the directly acyclic graph and a topological sort need to have V plus E, and initialized is V plus E, forward loop is V plus E. And since depending on most of the case, the OE, which it is in the asymptotic order, larger than OV, right? So this reason many of chapter, many of textbook, they just use OE to represent. And you may see in some case, maybe what you have the V larger than E. In that case, we say if there is a tree structure and E is equal to n minus 1, right? And if this is for the tree, the connected components is the smallest number for that, for the connected components. And if n is smaller than E, in that case which is not a connected component. Okay, good. I think we finished the shortest path in the DAG. I'm going to give you another video and talk about the digest algorithm for shortest path.